All right, welcome to the Explainer. Now, I'm going to make you a promise. By the end of this, quantum physics is actually going to make sense. And we're not going to do it with a bunch of crazy math. Nope, we're going to do it with a story. A kind of detective story, actually. The story of the atom.
So, where does our story begin? Well, it starts with probably one of the biggest questions humans have ever asked. What is everything made of? I mean, really, think about it. If you take something, anything, a chunk of gold, a single drop of water, and you cut it in half, and then you cut that in half, and you just keep going and going, do you ever stop? Is there a point where you just can't cut it anymore?
Well, the idea that yes, there is an endpoint, that's been kicking around for thousands of years. But here's the crazy part. For something like 2,000 years, that's all it was. Just an idea. You know, a cool thought exercise for philosophers, but there was no way to prove it, or disprove it for that matter.
So that's what we're going to do today. Here's our roadmap. We're going to follow this trail of clues, starting all the way back with an ancient Greek idea, and see how it leads us into the super weird, absolutely wonderful world of the quantum atom.
All right, let's get into it. Part 1, the ancient idea. We're rewinding the clock way, way back to ancient Greece. This is where the first clue in our detective story really shows up.
So picture this. It's the 5th century BC. There's this philosopher, Democritus, and he has this mind-blowing thought. He's the one who said, hey, if you keep cutting that piece of gold, you're going to hit a point where you just can't cut it anymore. You'll get to a final, fundamental piece. And he gave it a name, atomos, which in Greek literally means uncuttable. Pretty cool, right? But here's the thing you have to remember, and it's a big one. This was not science. Not yet. There were no labs, no experiments, no way to test it. Democritus just had a really, really good argument based on logic. And his idea had to go head-to-head with other big ideas of the day, like everything being made of earth, water, air, and fire. And well, for about 2,000 years, the idea of the atom just kind of sat there.
Okay, now let's hit the fast forward button. We're jumping ahead 2,000 years. And this is where the atom finally gets its big break. It's moving out of the philosophy department and straight into the science lab.
So, in 1803, this English chemist, John Dalton, basically finds this ancient idea collecting dust on a shelf, pulls it down, and says, you know what, I can work with this. He gave it a real scientific backbone. His vision? He pictured atoms as these tiny, solid little balls. Just think of them as microscopic marbles.
And his theory, it was simple, but wow, was it powerful. He said that all the gold marbles are exactly the same and they weigh a different amount than all the silver marbles. And here's the game changer. This was the first time anyone was using actual experimental evidence to talk about atoms. The uncuttable idea, the atomos, was finally a real scientific thing. But you know how science works, right? It never stops. The story's never over. People almost immediately started to wonder, okay, so they're solid marbles, but are they really indivisible? Could there be something inside? And sure enough, in 1897, a guy named J.J. Thomson was playing around with these things called cathode rays. This is basically the tech that powered your grandparents' giant old-school TV. And he discovered that these rays were made of something bizarre. Tiny, negatively charged particles. And get this, they were 1,000 times lighter than the lightest atom they knew of.
So, wait a minute. These new particles are negative, but atoms overall are neutral. Thomson put 2 and 2 together. He figured the atom must be like a ball of positive pudding, or dough, with these little negative things, which we now call electrons, stuck inside. Kind of like raisins. And just like that, for the first time ever, the uncuttable atom had been cut.
And then, in a classic case of the student surpassing the master, Thomson's own student, Ernest Rutherford, comes along and just completely wrecks the plum pudding model. His experiments proved that the positive charge wasn't some spread-out goo. No way. It was all packed together in an unbelievably tiny, super dense center. He called it the nucleus. And the electrons? They were orbiting it, like tiny planets flying around a sun. And Rutherford, he just kept digging. He figured out that the nucleus itself was made of these positive particles, which he named protons. But there was a puzzle, a mystery. He did the math, he added up the weight of all the protons, and the nucleus was still too heavy. It didn't add up. So he realized there had to be something else in there with them, something with mass, but no charge. He had just figured out the existence of the neutron. So now we have this awesome planetary model, right? It looks good, it makes sense, and there's just one tiny problem. According to the laws of physics, as they knew them,
It was completely impossible. It had a massive, fatal flaw. Okay, so here's the problem. Physics 101 says that opposites attract, right? And it also says an orbiting charge, like an electron, should constantly be giving off energy. So, that little electron should be losing power, spiraling inward, and crashing into the nucleus in, like, a split second. But, obviously, that doesn't happen. Atoms are stable. The universe exists. So, what gives? Why don't they collapse?
Well, the key to unlocking this whole mess came from a physicist named Max Planck, and what he discovered was absolutely revolutionary. He found out that energy isn't continuous. It's not like a smooth ramp you can slide down. It's more like a staircase. You can be on step 1 or step 2, but you can't be in between the steps. Energy only comes in these distinct little packets, and he called them quanta. I love this analogy. Think of a beam of light not as a steady stream of water, but as a bunch of tiny Amazon packages being fired at you. Each package is a photon, one quantum of light. You can get 1 package, you can get 2, you can get 100, but you can never ever get 1.5 packages. Energy comes in chunks. It's quantized. And this is where Niels Bohr had his brilliant aha moment. He took Planck's staircase idea and applied it directly to the atom. He said, what if electrons can't orbit just anywhere they want? What if they're locked onto specific steps or energy levels? They can't spiral into the nucleus because there are no steps in between for them to follow. The only way for an electron to jump up to a higher step is if it gets hit by a photon package with the perfect amount of energy to make that exact jump. Okay, so Bohr's model was pure genius. It basically saved the atom and laid the foundation for all of quantum physics. But our detective story isn't over. There was one last, really, really weird, mind-bending leap required to get to the picture of the atom we have today.
Then this guy, Erwin Schrödinger, comes onto the scene, and he suggests something so radical it changed everything. He said, basically, everybody, let's just stop. Stop thinking about the electron as a tiny little planet orbiting a sun. What if the electron isn't a thing at all? What if it's a wave?
In this new way of thinking, the electron doesn't have a nice, neat little orbit. It's not on a path. Instead, because it's a wave, it's kind of smeared out. All we can do is describe a 3-dimensional area of space where you're most likely to find the electron. It's not a path, it's a cloud of probability. And that cloud is what we call an orbital. And this completely bizarre idea that the basic building blocks of our reality aren't little specks, but are actually waves of probability, it sounds crazy, but it solved so many problems that had been bugging physicists for years. This is the foundation for pretty much all of modern chemistry, how we build new materials, and literally every single piece of modern electronics you own.
So is the electron a wave, or is it a particle? The mind-bending answer is somehow it's both. And that question right there, that's the central, beautiful, weird mystery at the very heart of quantum mechanics. Our detective story started with a simple question about cutting something in half, and it's led us to the strange new reality, which just makes you wonder what other unbelievable secrets is the universe just waiting for us to find.